small errors, just so it gets corrected. But it's basically correct, just small errors. Okay. So we have a region of space. So for this question, we have a region of space near the Earth's surface, below which we have no B fields. So we've got some y equals 0. And above that, we have a B field going into the page. And we've got a wire loop, which we are dropping. Now the wire loop is a square wire loop with resistivity rho, mass density. I'm just writing these out because they decided to call them rho m and rho, so that could be a little confusing. And then the diameter of the wire is given as d. D equals d. That's good. Diameter equals d. So if I take a cross section and draw it out, then it has a diameter of d, and the side length is L. Okay, so A is an easy one to answer. So while the loop is perfectly immersed in the magnetic field, as it falls, determine the drag force when, on it at the moment when its speed is v. So, so the force due to the magnetic field is Q, so I'm just going to call this F mag, is QV cross B. So that's for a charge with a velocity v. Now this can be rewritten as I dx cross b. And so if we have a current, now to figure out what current is going to be flowing, we would need our EMF. So our EMF is going to be minus d phi by dt, where phi is our flux. So our phi is B dot A. Okay. And so in this case, when it's fully immersed in the field, then we have our B field, which is constant and into the page. Our area is just L squared, so BL squared. And so then our EMF is minus d phi by dt, which none of these depend on time, so it's 0. And so then our EMF is 0. Then our EMF is equal to our current times our resistance. So then our current is 0. So we have no current flowing when it's fully in the field because nothing's changing. And so because we have no current flowing, then then our magnetic force is 0. Okay? Now, now that we have that, if we now, while the loop is perfectly immersed as it falls into the zero field region, determine the drag force when its speed is v. So I think I maybe I'm just gonna do it for I'm just gonna do the drag force while as it comes out of the zero field region. So our F mag is 0 up until up until it essentially reaches this point. And then as we start to move in, so as we start to move the loop into the zero field region, that's when things start to happen. Okay, and so now our phi is still b dot a, but our a is now just the area enclosed by the b field. So it's L on this side, but then on this side it is, and we're going to give it a speed v. So it's falling with a speed v, which is changing with time due to its acceleration. But it's falling with a speed v. And so this length here is actually L minus v delta t, or v dt, if you will. Or even better, just to make everything seem more reasonable, L minus vt. Right, so that distance is L minus vt. Now we're assuming that we're starting at time equals 0 when it's right at the y equals 0 point. Okay. So then our phi with this expression is then b, as our b field's constant and parallel to our a field, then our area is L times L minus Vt, like that. And so then our EMF is minus d phi by dt, which is going to give us BLV, just BLV, right? Because this is B times L squared minus LVT. Okay, and then the derivative of this with time, this part's not going to depend on time, and then this part does. So we're just left with a BLV. Okay, and our current, or our EMF, is positive, meaning that is our flow of positive charge, or our current, is going to be that way around the loop. we can double check this with some of the rules we know, as we know that our force is going to be I dx cross B. So we can use the right-hand rule. So if our current is running to the right from the top, and we put our palm in the direction, so we put our fingers in the direction of the current and our palm in the direction of the magnetic field. So our fingers in the direction of positive current, so flow of positive charge. Our fingers in the direction of the flow of positive charge, our thumb in the direction of the B field, then our thumb points in the direction of the force, so the force will be upwards. And we know that the current generated will be to oppose the motion, and this indeed imposes the motion of it leaving the B field, and so that makes sense. So our direction that we get here makes sense, and yeah, so that all looks good. We can solve for our current by saying that it's the EMF over the resistance. We can calculate our resistance for our wire from our resistivity by the length of the wire times the resistivity over the area, our cross-sectional area. So our length is 4L, our resistivity is given as rho, and our cross-sectional area is going to be pi r squared. Now our radius can be computed from our diameter over 2, as we're given the diameter for our wire, or we're given that we know the diameter d. So it'll be 4L rho over pi d squared over 4, which is just 16L rho over pi d squared. And these are in terms of constants that were given in the question. So now we can plug in some of our values here. So our current is going to be BLV over 16L rho over pi d squared. We can cancel these L's and bring the pi d squared up top. So BV pi d squared over 16 rho. And so then there is our current. Okay, so that's our current given a velocity v. And so then our force, which so our force on some dx I've given as I dxb in this direction. So our total, so that's our small increment of force. So our total force will be the integral. Now if we look at the current just from the top, or if we look at the force just along the top, then we're going to integrate over the length. So our force is just going to be I B L, so we're just integrating over that length. If we look at this length here, well then our current is going down. We use our right hand rule, so the force will be outward this way. So we do have a force in that direction, but it's perpendicular. And if we look at this side where our current is flowing this way and use our right-hand rule, then we'll see that the force is going in the opposite direction. So these two actually cancel, and then there's no force on the bottom of the loop. So in other words, we only need to consider the force at the top of the loop, as that is going to be our only contributor. So that is our magnetic force, just IBL. So then plugging in our our value for the current that we just calculated, so B V pi d squared over 16 rho times B times L, or B squared V pi d squared L over 16 rho. And so then that's our magnetic force. And okay, so then and so that's our magnetic force. So that's our full answer to A. There. Okay, and now if we look, so when we're looking for a terminal velocity now, so we've got our loop falling with some velocity v. We look at our forces, we have mg and f mag. So our f net is b squared v pi d squared L over 16 rho minus mg. And in fact, this equals ma. Our terminal velocity is when ma equals 0. So when b squared v pi d squared L over 16 rho minus mg equals 0. And so we want to solve for our terminal velocity vt. So first of all, we were told that our mass, that we have a linear mass density rho, or sorry, not a linear mass density, but a mass density rho. So our mass is going to be our length of our wire times our cross-sectional area, which we're given d's. Diameters, so cross-sectional, still got a cross-sectional area, but we're given the d, so d over squared, d over 2 squared. Just rewrite that to be a little bit clearer. Times our linear mass, our mass density, not our linear mass density, but just our mass density. And so then our length is 4L times pi d squared over 4 rho m. So the 4's will cancel. So pi L d squared rho m. So that's our mass. And so then we're just going to use that in this expression above and solve for our terminal velocity. So first, moving things to either side of the equation. And then we can cancel the pi, cancel the d squared, cancel the L, and then solve for our terminal velocity. So Vt is equal to g over b squared times 16 times our resistivity times our mass density. And just to be sure that I didn't make a mistake there, there it is. Yep, so that looks good. So there's our terminal velocity in terms of the values we're given. Okay, and then so C is find our terminal velocity if it's made of copper and our B field is 0.80 Tesla. So if we're made of copper, then we can look up these values and find that our mass density is 8.96 grams per centimeters cubed, which we can convert to kilograms. And convert our centimeters to meters, so 1 times 10 to the 2 centimeters per meters cubed. And we get a mass density of 8,960 kilograms per meters cubed. And we can look up our resistivity for copper, which is 1.68 times 10 to the minus 8 ohm meters. Okay, yep. And so then our terminal velocity is 9.8 meters per second squared over our B field, 0.80 Tesla, times 16 times our mass density times our resistivity, 1.68 ohm, 1.68 times 10 to the minus 8 ohm meters. And so the value comes out to be this should be B squared, so that's squared. 0.0369, and this would be in, if we're following along here, ohms. Looks like ohms, kilograms, meters squared per Tesla squared, second squared, meters cubed. So the meters squared will cancel there. I have this here. A Tesla is a kilogram per coulomb second. A ohm is a kilogram meters squared per second coulomb. Might be seconds. Coulomb squared. Yeah, coulomb squared. So then, yeah, okay. So then this is in 0.0369 kilogram meters squared per second coulomb squared times kilogram per second squared meters times coulomb squared second squared per kilogram squared. So this is the ohm unit. This is what's left, and this is the Tesla squared unit. And so we can see that the coulomb squared will cancel, The second squared will cancel. The kilograms squared will cancel. And the meter will cancel, leaving us with 0.0369 meters per second. All right, so just a quick unit analysis to make sure we didn't make any mistakes. So it doesn't look like we did since the units all work out. But let's check our solution with what's given here. And so there's our induced EMF. And so there's our resistivity. There's our current. Our dA dt is just LV. And so the current is going to be BV pi d squared over 16 rho. Oh, they just didn't cancel the L, so that's okay. And so then we get an L up top, so there's our magnetic force. So again, that looks okay. Our magnetic force is going to equal our mg. So our terminal velocity is, so that looks good. And then using values that we look up, 8960, so that's about the same. 1.68 10 to the minus 8, so that's good. And it comes out to be 0.037, so yep, that looks pretty good. All right, so say solution is correct. Looks good.